with relations over here. And then again, they are more like a function over here. But the important point is that they can have some cross product of the sets as an input, or you can say domain. And again, they end up with some sort of, true and false at the end of the day. So this means that if you talk about predicates, so they can be any sort of, they can have any sort of arguments. But in the case of relation, guys, they are somehow relating those input arguments that you are taking. We can say that you can write any sort of function where it is somehow representing a relationship between different objects, between different input arguments of the function. So the very simple example from the maths would be greater than function. Greater is somehow a relation that is taking two arguments, which is A and B, and it is telling us whether A is greater than B or not. And similarly, you can have an equal relation as well. So further digging into these binary relationships, we have some properties as well that are, somehow quite important properties. So one is reflexive. So it says for all x, x or x. R is our relation. That can be any relation. And this would hold always for all x. So this means that for all. So for all x means that if x is some sort of natural number, so it is true for 1, 2, 3, 4, 5, up to so on and so forth. This is what we mean by for all over here. And then x or x means this is true for all x. Now I would ask you guys to put any function R over here, any relation R over here, so that this property gets true.
Equal to, sir?
X is equals to x.
Perfect. Yes. So that would be equal to. I say 2 is equal to 2, 3 is equal to 3, 4 is equal to 4. So this means that for equal to relation, this reflexive property holds. This less than equal to means that it can either be less than or equal to. So when you place or over here, so that means that that equal to thing would make it true. And another important property is symmetric property. So symmetric is something you are somehow equating some right hand side and left hand side over here. So it says for all x, y, x or y implies y or x. If x or y is true, and then you can say y or x would also be true under symmetric property. No, again.
Addition or multiplication?
Yes, but we have a lot of relationships. So you said it rightly. So we have addition as a relationship that would hold true for the symmetric property, and then we can have multiplication, and again we can have equality as well. If I say x is equal to y, or if I say y is equal to x, so both are true. And then we can have transitive property. So it says for all x, y, z. So we have three variables now. If x or y and y or z is true, you can say x or z is also true. Okay, so we can have some equal to here. And what else?
The greater than, less than.
Yes. Now greater than and less than would also be true for this case. Now let's move from these functions to these graphs. And you can see these graphs. These are some sort of random graphs that I have taken for you guys. And you have to observe something in these graphs. You can have some sort of numbers or labels over here. This is 1, 2, 3, 4, 5, 6. There are some arrows over here. You call them as edges maybe. And you can't see any sort of arrows over here. So these are different sorts of graphs. So what exactly a graph is? Graph is somehow a combination of vertices and edges. You can call those vertices as nodes as well. If you talk about nodes or vertices, so these are the vertices over here. 1, 2, 3, and then 4, 5, and 6. And, these are the edges. This is the edge, this is the edge, this is the edge. So edge is somehow connecting one node with the other one. That's a simple thing that you have to keep in your mind. And you are getting some direction for these edges as well. So you see, you can't have direction for these edges. So this means that you can either go from here to there, or if you are standing here, you can go to there as well. So this is some sort of undirected edges, I would say. Got this point? So graph is always composed of two major things. One is edges, the other one is nodes or vertices. Now we can have some directed and undirected edges as well. So I just identified, if you talk about the first graph that we can have, all those edges are directed one. And for this one, all edges are undirected one. And then we can have labeled and unlabeled node as well. If you talk about this first graph, you can see these nodes are labels. I gave them names, 1, 2, 3, 4, 5, 6. But if you talk about this one, so these are the unlabeled nodes. I didn't give them any sort of labels. So that's why I can declare these kinds of nodes as unlabeled nodes. If we have a larger graph over here, and then we can have some chunk of subgraphs out of this one. You can see subgraphs in the graph 2 as well. And these have been shown in bold lines. So this is somehow one subgraph. Now we have undirected edges. So you can either go from here to there, or you can go from here to there. So this is the advantage of undirected edges. You can go from any direction to the other one. But if you have some directed edges, you have to start from the tail, and then you have to go to the head of the arrow. So we can have some paths in the graph as well. You can see, I have somehow highlighted this path. I can start from here, I can go there, and then I can go there, and then I can go here as well. So this is known as path. I can have one more path as well, maybe this one, and this one. So all these, nodes that are connected by edges, these are known as paths. And then we can have cycles as well. Now cycle is somehow you are starting from first node or one node, and then you have to come back to the same node. That makes it one cycle. You saw this is the path, and then you are starting from this node and you are ending on this node. So your start node and end node are not same. That's why you declare this as path. But for the case of cycles, your start and end node should be same. This means that you are somehow completing some sort of closed loop, closed path. That is known as cycle. So this is the difference between path and cycle. Then we can have connected and unconnected graphs. Connected as obvious from its name, so all those nodes would be connected with each other. So if I consider this as one graph, so is it connected one? Yes, it is connected one. So if I change my problem, if I take both of these graphs as one graph, so whether they would be connected or not? They would be unconnected because there isn't any sort of connection from this subgraph to this one. There isn't any sort of connection. That's why you call this kind of graph as unconnected. So for the graphs, if you pick a node, which is somehow looks like this one, and you can see some incoming edges on this node. You are connecting different nodes, and then you can have some directed edges as well. Now, if you calculate the number of incoming edges towards a node, that is known as in degree. So if I talk about this example, what is the in degree of this node? So this would be simply 3 for this case. And if you talk about out degree, guys, so that would be somehow a number of, that arrows that are going outside that node. This is somehow known as out degree. So it is quite obvious from its name. So we have in degree, and then we have out degree. So what is the out degree of this node? Okay, so it is again 3 for this case as well. And if you talk about binary relation, guys, so you can represent that with directed graph as well. If I have a relationship which says A or B, and this is my R, and this R is relating A object with B object. So I can represent this with graph as well, binary relationship. Okay, this R can be anything that is true for this A. Let's go with activity, guys. This is your activity. So you have to write in degree and out degree for each node of the following graph. And then you keep on filling that table in that, the in degree, out degree.